Hello and welcome back to another festive coding session with Mr. Jacob. Today we want to tackle another of our Advent of languages where we strive to implement in the 24 first days of December the same thing in another language each day. And what we are going to implement is some sort of representation which prints out kind of this ASCII Christmas tree, or in cases of graphical languages that we tackled before as well, we might implement that in a graphical way. Today's language of choice is Ada. We will implement this in Ada, which is a very structured, kind of safely and strictly typed language with a lot of different concepts from object orientation and a little bit of functional style in there. However, it's a very declarative language where you have a very extensive syntax in the language itself to make it as speaking as possible, so to say. So as always, I have prepared a little build environment for me here. I have created a very minimal Docker file here to actually install the stuff that we need to build our Ada files. And I have created myself a make file here, which kind of only takes the make, the main entry point, which we will call main.ada or main.adb specifically, which is meant to be an Ada body file, because we will kind of have declaration files, ADS files, which are header files. However, it takes this main file and simply compiles it for us in the Docker image. If the Docker image is not there, it will build it first, because I don't have an Ada compiler on my system here. So that is what we are going to use. Everything else we will now create. So let's start by simply creating our main ADB, so our Ada body file here. And what we first need is a way to actually output something. So we are importing the Ada text IO module, or part of the library, the package, so to speak. We are actually importing the Ada text IO package, which is part of the Ada standard library, so to speak. And now we will simply declare something like we will have a procedure, which will be our entry point into the system, that is called main. So we have procedure main begin, and you will already see something with the casing here, which we will no, it is sorry, procedure main is, and then we will have a begin here somewhere, and then we will have an end main at the end. And as you can see, all of this is already kind of very explicitly defined. So if I want now to output something, I could say I want to use this package put line function, and say hello Xmas, for example. And let's first check that I haven't done something wrong, because I'm not that fluent actually in Ada. But we have our hello Xmas here, which is kind of nice. So this worked. So let's take a further look at that. First of all, the naming scheme of Ada is a little bit interesting. It's kind of a camel-cased version of snake case. So you are using camel cases, but you are using underscores to differentiate different things as well. So that's kind of interesting, because that is actually called Ada case as well, because it is that kind of special to Ada. So you will see that naming here a lot. The next thing that you can see here is that I needed, even though I imported this here with Ada text IO, I needed to fully specify what I wanted to use from this text IO package. That is because Ada differentiates between loading a package and actually making it or using it within your current context. So if I would have done that again here and told it that I want to use Ada text IO as well, then I could have removed this forward, or this full name declaration here, and it should work as well. And as you can see, it does. So that is more or less the absolute basic that you need to know. That's why you often see something like that. It will be often formatted in one line in projects where we have this with something. So to load the package, and then use to actually use the package, to import it there, to be used without its full namespace declaration. Okay, so now after we have done that, let's take a look at how we can actually print our tree. As always, we need something that kind of prints our groups first. Let's maybe get in our tree here just to see that we have something there that we can actually reason about. Let's wait a second. Yeah, there's my tree. Then we could remove those and let's comment those out. As you can see, the comment character in Ada is 2 dashes there. And now we have our tree here. I did not remove all spaces there. Yeah, okay. I think we can live with that just to have this as a reference. So first of all, we need to kind of print always these groups. So this one and this one and this one, because the zigzag shape is created kind of in groups. And we have in this tree here, we have 3 groups actually. So let's start creating a function which actually could output one of those groups. So something like a procedure, maybe something like a procedure that could be called print group. I guess that is reasonable, and we can give it parameters. We can give it an n. So actually, the group that is currently printed, because we need it to calculate spaces, and this will be a natural number. So it will be a positive kind of integer number there, and we will give it a length, which will be a natural number as well. And this thing is, again, some sort of function, and we can do begin here and end here, and we need to specify at the end what we are ending to ensure that we are always have this this proper definition where we can see the start and the end of something without checking kind of open brace, closing brace, open brace, closing brace. Actually, this is a little bit verbose, but you get used to it. We will see in a second that this declaration, what I'm doing here, is not 100% correct, but I want to explain to you why. That's why I'm writing it like this currently. So if you know Ada and you are screaming at your screen now, please bear with me. I'm not an Ada expert at all, but I will be able to create, hopefully, a working program together with you in the end. So let's see, how could we actually do this? We need some sort of spaces there. So we will do something like, I guess, put line here. And we want to kind of do something like, for example, we will in the end have 2 lines because our groups are always 2 lines. So we will have something like, for example, outer spacing 1. For example, and then we want the slash character here. So how do we concatenate strings in Ada? We can use the ampersand character. So that's what we are using to concatenate strings here. So we might do something like this, and we will then have something like inner spacing 1. And in the end, we need a backslash. And there's already something kind of interesting you see here. I did not escape this backslash. In, I guess, all other languages that we looked at before, we needed to do this. However, this is in Ada 2 backslashes in a string, because Ada does not use backslash escaping in strings. That's kind of an interesting thing. The only thing, as far as I know, that is really kind of escaped in strings is the quotation mark. So in order to do a quotation mark, I need to do 2 in a string, and Ada will simply print this as 1. That's, as far as I know, the only thing in a string that is kind of escaped. Everything else needs to be constructed in another way. So now we have this outer spacing 1 and inner spacing 1 here. Let's quickly copy this line and make it an outer spacing 2 and inner spacing 2, because as I've said, we have always 2 lines with different spacing sets, and we need to somehow calculate them. So how would we actually calculate them? I guess we need a variable for that. And in Ada, a variable needs always to be defined in a specific block. So you always have this body here separated from the variable declaration. So in a procedure, for example, you can have something between this is and the begin of the function that actually defines something for this procedure scope. So everything that is defined at this point is valid for this begin and end scope in the whole function. You can actually have a declare block, which you could put in here, and then you could do something like declare something something here and then begin and end again, and then you would have only for this scope declared something. It's more or less block scoping in other languages, however a little bit more explicit. So what we are doing here now is we are defining our outer spacing 1, and our outer spacing 1 will be a string. So we are defining it as a string type, and we tell it that, yeah, what do we want here? We want to call another procedure or function there, specifically a function, which we will create in a second, that we will call make space. Make space sounds nice, I guess. And we will want to know how much space we want there, so we will supply that. And for the first outer spacing, that would be the length minus n. That would be the amount of space that we need. And we need inner spacing, of course, as well, inner spacing 1. And this would actually be n times 2. So that is what we need here. We can see that if you take a look at the tree, how this actually corresponds to our groups that we are currently creating there. And then we, of course, need the same thing for our second line. And this time it will be 1 space less on the left, because we are going 1 further to the left. And we will have in the middle n plus 1 spacing here, because we are actually n plus 1 times 2. We are actually taking the spacing from the first line of the next group there. And now we have defined all that. We need some sort of function which creates us those space strings. So let's define one. And this time it will be a function, because there is a difference between a procedure and a function in Ada as well. That is a little bit verbose, but it is to be most precise. A function is something that is supposed to have no side effects. The compiler will even warn you in some situations. And it's kind of supposed to only have a return value. A procedure can't have a return value, as far as I know, or it should not have a return value. At least that's the way of doing Ada. A function, however, is allowed to have a return value. It is not allowed to have one. It kind of must have one, because it is something that should be side effect free. And otherwise, a function wouldn't make a lot of sense. So that's more or less the difference between a function and a procedure in Ada. So what we want to do now here is we want to define a function called make space. And this function takes, of course, again, a natural, because we want to define the number of spaces that we want, and it should return a string. And now we have an is here again, and we have a begin, and we have an end make space. So the basic syntax is the same, but the ID kind of the declaration type here is a different one. So how will we actually do that? The string type kind of has the possibility to be handled like more or less an array. So we can use the array initializer structure. It's not called that in Ada, and I'm not 100% sure about the mechanics that are working there internally. But what we can actually do here is we can return something where we say, where we use some sort of implicit array structure or list structure declaration syntax. So what we could do here is we have different ways, of course, to do that. And I want to show you 2 of those. We can do something like, we can now say we want a list here which goes from 1, because lists in Ada are strangely always starting at 1, not at 0, which goes from 1 to our n. So that we actually want that, and we want for all of those entries, we want to put a space in there. And that would actually in the end be a string which contains all spaces. It's essentially the same thing as we would have done something like we want the first one to be a space, and we want the second one to be a space, and we want the third one to be, third one to be a space. I think you get the gist of it. So that's essentially the same thing, but in a more specific syntax, which then can go to an arbitrary value that we give it here. The other possibility we could have done is we could have used something like we could have created a variable here called, for example, spaces, which is a string, of course, and it is then defined as no, we could have defined that, we could have defined that as a specific string which has the length of n characters here, and then we would have filled it up here doing something like, and I'm not 100% sure the syntax I'm currently writing is not perfect, but we could have done something like that we specified others here now, and then you could have done this, something like this. Not perfectly like this, but more or less, because in Ada there is this syntax of others, which is quite nice. You can use that every time you have this parameter list of sorts. So if you want to specify everything else that I now give you here, which I haven't given you here, so we could have done something like, for example, this, then the first character would have been an X and the others would have been a space. So everything else that I've not given you here, set it to this corresponding value. You can usually use that in data structs or records or stuff like that as well, by, for example, initializing to the default. That, for example, is the default value in Ada. Okay, but that is not really relevant for our function now, as this should actually create us a string with n spaces. So we should now have our make spaces function here. So let's maybe try and go ahead and simply print out our first group. So print group, let's say we want 3 or 0, and we want from 3. So we have this print group here, and when I now compile and run that, you will see that it will not work. So it actually tells us, and that is kind of interesting, and a file expected. File can only have one compilation unit. So what you only can have in Ada per file is you can only have one package, one procedure, one function, one anything, so one compilation unit. So how do we actually fix that? We could now move everything that we did here, like print group and so on, into another package, into another file, where we then package that up as a package, actually, by doing something like package xmas xmas tree is, and so on and so on. Yeah, you get the gist. However, what we can do, and this might look a little bit strange, but that's why I first showed you this declarative syntax here between the is and the begin, we can simply take all of those functions here and put them into this main procedure. So they are now part of the declarative block of this main procedure. So we tell it that we have a procedure called main, which is the base entry point here, and we define all of those functions to be block scoped to this main function here, where we then use that simply, and that works quite well. So now hopefully this compiles. Of course it doesn't, because I have done a lot of stuff wrong here. Let's see. So what did I do? 18 should be a semicolon. Yes. Okay, let's go through those errors. There should be a yes, that's because in Ada arguments are separated, function arguments are separated with a semicolon, not a comma. I always do this wrong. I already see that I've done something wrong here, because the setting of a variable is always done with this colon equals define syntax. So let's try again, make run. And as you can see, we now have our first level of our Christmas tree. That's already quite nice. So let's go ahead and create the other levels as well. So let's maybe define another procedure here, which we could call procedure print groups. So we want actually the length here, which is a natural, and we have this. What? No, is not. What did you autocomplete there, Vim? And we have a begin and we have an end print groups. And in this one, we simply do a for loop. So we say for n, for example, in, and we tell it that we want from 0 to length -1, because it is always inclusive. And now we tell it to loop. And how do we end this loop? We do an end loop. So as you can see, as I've said, Ada is kind of verbose, and everything is quite explicit. So we are really doing that always with this end and begin, and specifying what we are actually ending there. So now what we need to do here is we need to simply call print groups with n and the length, I guess. So this should more or less do it, and now we should be able to do something like print groups 6, for example. Let's see. And of course it doesn't, because I still did something wrong. Line 33. Yeah, we have to put a semicolon there after. More or less after each of those statements, all of those are kind of ended on a semicolon, and Ada is kind of strict about that. So too many arguments in call to print groups. Wait, what? Yes, because I called the wrong function here. I should have called print group and not print groups. And now, as you can see, we have part of our Christmas tree. So let's quickly add the rest of the Christmas tree there, or maybe we could kind of stop here drawing the Christmas tree and do something about adding random ornaments there to show a little bit of different parts of Ada and how we can actually define a package. Maybe we'll do that. We will only create half a Christmas tree this time. So let's see, how could we do some randomness here? First of all, we need something that is a random generator. So let's quickly start a new module here called random.ads in this file, because we want to define a package. We just start a package, not a module. So what I do here now is I tell it that I want package random, which should be something, and I want to begin and random as always. So I want to create our own package. Why do I want to create our own package? Because randomness in Ada kind of needs a state in form of a random generator, and this random generator needs to be somewhere where we can easily access it and use it in, for example, different situations of our application. And that's why we put it in a different package, because we can have package-wide fields which we can then use. But first of all, we need this ADS file, which is a package declaration. You can think of it as a kind of a header file, something that defines the schematic, the schema of your package. So what we want here is we want to first define some sort of function, which we expose then later on. Everything that is specifically defined here is public if you do not put it after something like a private. So you define private here, and everything that is now here will be private, but everything before will be public. So we want something that, for example, calculates a chance for us, because we are always doing that, like with 20% chance do something. So let's quickly get this function chance to go there. Let's do maybe a percentage here, percentage, which would be a float in this case. And this one returns a Boolean, and it is defined as, we will see in a second how we define that. What we further need, we are not defining the body here. We are still defining only the interface. So we are defining the interface, which also contains this procedure, which we call simply initialize, which will not take any arguments, and it will in the end initialize our random number generator. So let's store that and let's go to the body file here, random.adb. So we do the same thing here, kind of package. However, now we define that we are defining the body. So we say package body random is, and we can begin now and end now. Here are the same thing. So let's quickly get our random declarations over here so that we can more easily fill them out. And then we now can do something like we want to begin here and we want an end chance here and we want to procedure initialize. Come on is begin and end initialize. And what we want now in our module here, in our package here, is the random number generator. So we simply can, first of all, import that one. It would be Ada numerics, I think, and then something like float random. That should do the trick. And now we can define something like we want something here in our module, which is of type Ada numerics float random because no generator, sorry, because generator is the thing that we need as a state kind of to our randomness thingy here, and we simply define that here, and then in our initialize we can actually initialize that value, and all of the things that then like chance are called there can access the same thing in our package. So we will do something like, I guess it was reset. It was Ada numerics float random reset, and we are now simply resetting our random number generator. I'm not sure if we need to initialize it. We will see in a second. So that's essentially everything that we need to do to initialize it with a new random seed. We could actually provide it here with some sort of seed. However, we want just the random one, so that's fine for us. And now for our calculation here, we can now use our generator. We can do Ada numerics float random, and I think it is just random, if I remember correctly, and you give it the generator, and then it will give you a float between 0 and 1. So what we do here is we simply say that we want to return this number, and we want to return if it is less than our percentage divided by 100. To just move it to the range of 0 to 1 as well. And so if we are in this range, we can return true, and otherwise we return simply false. This should actually kind of work, even though I'm not 100% sure about this here. So let's see if this compiles. I'm not so sure that it will. It actually compiled, but we never told our Ada system, our Ada application, that we actually wanted our random package. So we are now including it here. So this will now include our own random thingy here. So let's see what happens now. Now it should be compiled, and now, of course, this does not work. Begin block not allowed in package spec. Okay, maybe I did something wrong there. So random ADS, let's take a look. Yeah, the begin is definitely wrong because we are not giving it an implementation. That is right. And I think I did that wrong here as well, didn't I? Yes, I did that wrong here as well, because those are all declarations. So they are kind of part of this declaration block that we had before. But what's the problem now? Okay, now it's not. Now it's complaining about a missing semicolon. So let's check if we have done something wrong here. Yes, we did not have a semicolon at the end. Let's make that run. Okay, that now compiles. Definitely now works. So let's see if we can actually use it. Because what I want to show you actually is that we want to use Unicode now. And as we want to use Unicode, we cannot use normal strings in Ada anymore, but we need wide strings. Ada essentially has strings, which are 8-bit ASCII characters. It has a white strings, which is 16-bit Unicode, and it has white strings, which is actually 32-bit Unicode. So what we now need is here, we need to kind of convert all our used strings here into white strings to use Unicode in the end. So we can use white text IO. So let's use white text IO. And we need, of course, use a white string here now. So this should be now a white string. And let's see where we are using string. There we are using string as well. So we now need to, of course, change those type declarations to be a white string. And this should still, I hope, compile and run. It does. So now we are actually internally using 16-bit Unicode strings. So now we can do something about, for example, creating ornaments. So what we can do now is something like, for example, make ornaments, or make ornament maybe, and we give it the usual count here, and it will return a white string, and it is something here. And now we will have some definition there in a second. However, let's first of all make this function complete here, this function declaration. So what do we need here now? We need, I guess, something that is an ornament or ornaments. Let's, as the time has gotten quite far, let's just put one ornament there, something which is a white string, which would be something like a star, for example, or something like that. And we could do then we need something where we now can kind of build our string dynamically in. And for that we need an unbounded string. So we need something like with Ada strings, I guess, unbounded, something like that. I'm not 100% sure, but we need white unbounded. Well, let me quickly check what we need there, actually. I've opened up the reference manual here. So wide or let's just check unbounded length string handling, because we need, come on, open that up, please. Okay, so it is Ada strings unbounded, and I'm quite sure then there is something like wide. I guess it was then, it's either wide string handling. Let's see, Ada strings wide. Yeah, I guess it's wide unbounded then. So let's just go back to our, come on, code here. Most likely this will be correct. We will see in a second. So so now what we need to do is we need something like, we could call it builder or something like this, which would be a wide unbounded string, I guess. I'm not 100% sure there. And we could begin by creating one with two wide unbounded. And we simply start with an empty string there. And what we now need to do is the usual thing. We are just iterating, and for that we need an I variable here, which is an integer, or a natural would suffice, I guess, because all our others are natural as well. And it starts at 0. So what we now do here is we go ahead and tell it that we want to loop while I is less than n. We want to loop, and we want to end this loop in the end. And while this is the case, we are simply doing something like if random chance 20%, and I is less than n minus 1, because we need to stop one from the border, because our Unicode characters are actually 2 characters wide. So we need to incorporate that, otherwise the formatting will completely break. So if random chance and so on, then we want to do, did we actually, we did not. Let's use that as well. So that we have all of those unbounded string functions there. We want to append to our, what did I call it, builder. We could call that builder string or something like that. We want to append our ornament. And we want to do I is I plus 2. And otherwise, we would want to do more or less the same thing. However, we want to append a space here. And we want, come on, and we want only to add one character. And we want to do an and if. Okay, and I'm pretty sure this will not compile, but of course now we need to change this. We need to not make this make space, but make ornament, of course, in the inner situations here, ornament, and we need to actually initialize our random number generator, random initialize, before we are printing the groups. However, I'm quite sure this will not compile first try. Yeah. Missing return statement in function body in line 15. Okay, let's first check that. Yeah, that's actually kind of true. We never returned our builder here, which we should have done. And I guess we will need to convert our builder into a bounded string. So I guess we want to do something like to wide string. I hope this actually exists. We will see. So wide unbounded string is undefined. Too wide unbounded is undefined, and there is a missing semicolon. So let's fix that missing semicolon first. Yeah, there is a missing semicolon. Okay, so we did something wrong with our wide unbounded string. So that's actually not how we do that. So let me quickly check the reference manual again. So too wide. To wide string replaces to string. Unbounded wide string replaces unbounded string. Okay, so we want unbounded wide string, and we want there two unbounded wide strings. So let's go back and see. Strings. So we just did it in the wrong order. It's unbounded wide string and two unbounded. What was it now? Two unbounded wide or two unbounded wide string? Yeah, as I've said, Ada is very very verbose and explicit. Two unbounded wide string. So let's see. Does this now work? Okay, it at least compiles. So does it run? And there you can see we now have Christmas ornaments on our partial Christmas tree. We did not finish that up. However, that's kind of a way how you can define packages in Ada, and the way that we can actually use variables or package-wide data, like for example this generator here, which we put there. Ada has a lot of interesting concepts that we couldn't tackle in this session. Maybe we could do a project in Ada if you are interested in the future, which is a little bit more and bigger. I would be up for it. So if you are interested in that, please leave me a comment, and we will see in the future if we have time and a proper project for that to implement something in Ada, which is a little bit more sophisticated here. Because there are a couple of interesting concepts. For example, like you can have generic packages and generic types, and they work a little bit different than in other languages. As with all the other stuff in Ada, you explicitly have to then instantiate a new type based on this generic, and then you can use this instantiated new type. And that's actually something that's kind of nice in a way, and it's a little bit verbose on the other side. So as with many things in Ada, it's a little bit verbose as well as kind of nice. So yeah, I hope, even though this session was a little bit longer because we introduced all this random and package stuff and had some compile errors there, I hope you still had fun. seeing me do this and following along in our Advent of Languages. And I hope you will join me in when it is tomorrow again, the next day in the Advent of Languages, where we'll see another language. So yeah, I see you in the next one. Bye.